One important also parameter that will be extremely technologically important that is related to the density of the defects is the diffusion. So I would just like to spend a couple of minutes talking about the diffusion. Again, it's driven by the density of defects. So the diffusion simply means that if you have one particular material or difference in the concentration of the materials, because of that difference in the concentration, atoms will diffuse from one high concentration site to another. And it turns out that this rate is also dependent on the temperature, and it follows the Arrhenius law. So the rate, or how quickly this diffusion will happen, depends, again, it's an Arrhenius law, which will depend on the enthalpy of migration over kT. So again, we have the same form as in the concentration of the vacancies and other types of defects. The only difference is this activation energy, which is now enthalpy of migration. And again, we will see very soon that this, how quickly the diffusion happens or what is the rate, strongly depends on the number specifically of vacancies and other types of point defects, because the diffusion is driven by the presence of the vacancies. The vacancies are involved in this process. And again, the diffusion is relevant for many, many technological processes. For example, the ionic conduction, how quickly the ions can move throughout the crystal, or plastic deformation. And for example, diffusivity of gases throughout different materials. So these are all driven by the presence of the point defects and the diffusion processes. So what we will basically talk about is that we have two different materials, A and B. And we are looking at what is happening if you merge these two materials together and you change their temperature, or you introduce any type of effect that will enhance this diffusion. So what we are initially looking at is the concentration of the elements A and B. And in an initial state, on the left-hand side, 100% of the material will be A, and it drops to 0 at the interface between A and B. And on the other hand, on the right-hand side, the concentration of B is 100%, and it drops. So the question is, if you merge these two materials together, and after some time, or if you increase the temperature of this material, what happens? So the profile will look slightly different. So you will have 100% of A, and it will gradually decrease. And again, it will reach 0 on the right-hand side, but there will be this interface between the material where they will interdiffuse in between each other. The same thing will happen for B. It will be purely B on the right-hand side, but then the concentration drops toward the left-hand side. So the question is how quickly this happens, for which material it will happen, and what is the driving force. So for this process to happen, you need to have vacancies involved in the diffusion. And what that means is that if you have a starting point, if this was material A and this was the material B, if you imagine that there is a vacancy on the side of the B material, the atom from the left-hand side simply is replacing the vacancy. So the vacancy moves to the left-hand side, to the region of the material A, and effectively the atom A ends up on the B side. And again, you continue this process, but the important message is that this process of the diffusion is mediated by the presence of the vacancies. So higher concentration of the vacancies you have in the material, it's more likely that the diffusion will happen. Okay? Again, this tells you something about how these diffusion processes depend on the temperature. Also, we can talk about the interstitial diffusion. So it's simply if you have small interstitial atoms, they can diffuse throughout the material. And in this particular case, there is no vacancy intermediate step. So these atoms simply can move throughout the material. But again, how quickly they move will depend on the temperature at which the material is. So the flux, or how quickly, or what is the amount of the material that is diffusing over the surface area and over the time, will be proportional to the difference in the concentration. So what that means is that if you have a certain concentration of atoms on one side, and if you have a material on the other side that has the concentration C2, how quickly this process will happen depends on the difference between C1 and C2, right? So if they are roughly the same, then the flux itself will be relatively low, right? But if the difference in the concentration is very high, if you have much more atoms on the left-hand side than on the right-hand side, then the expected flux would be significantly higher. So what that means is that the flux is proportional to the concentration gradient. So I can write this that the flux is proportional to dc and dx. And this coefficient of the proportionality is defined by the diffusion coefficient. Okay, so, and how I write this is then that the flux itself is minus the diffusion coefficient d times dc dx. And if this, again, if the change in the concentration is linear, then this dc would be simply C1 minus C2, but you can imagine that these concentration gradients can be very different, okay? They don't necessarily have to be linear. So the question is, what is this diffusion coefficient? What does it depend on, etc.? But the first question that I can ask you is, why is there minus here? Why did I write this minus here? Yes?
Are they referring to the first area where atoms are being taken out? So, like, the change in atoms in a certain area is going to be decreasing.
That's right. So the answer is that this minus indicates the fact that the flux will go in the opposite direction of the concentration, right? So if you have higher concentration here than here, the flux will go in the opposite direction. So this is just the significance of this minus here. So I would just like to mention that this is so-called Fick's first law of diffusion, and it assumes that the composition or the concentration on the left and the right-hand side is constant. And a typical situation would be, for example, if you have a thin metal film, and then you have high pressure of gas on one side and the low pressure of gas on the other side, and then the concentration of these gas atoms is independent on the time. However, if you have two materials that are merging together, let's say, for example, in the previous case here, this concentration is not constant as a function of time. And this is described by a second Fick's law, and we won't go into details. There are other courses that you will take throughout your career, which we will go into more details. But in the first Fick's law, we are simply assuming that the concentration difference is constant. But these processes of the diffusion in, for example, metals are a little bit more complex because this concentration changes as a function of time. I would just like to mention that, again, the units for the diffusion coefficient is meter squared over second. And we will see that this diffusion coefficient is also thermally driven, or it's temperature dependent. And again, why would it be temperature dependent? So if I tell you that this diffusion coefficient follows the same Arrhenius law as what we talked about, for example, the vacancy formation, why would it depend on temperature? So I will just write what I just told you, is that the diffusion coefficient can be written as some constant d0 exponent of minus qd over RT, where the qd is the activation energy for this process. Why would it be temperature dependent, and why does it follow the same type of Arrhenius law that we described, for example, for vacancy formation? In other words, why is it more likely that the diffusion will happen at higher temperature than at lower? Yes?
As the temperature increases, like the atoms will have like a higher energy, so it'll be easier for them to move between like lattice spaces.
That's right, but why does it follow exactly the same relationship as vacancy formation? If I show you this picture here, any clues? Yes?
Well, at higher temperatures, you're going to have more vacancies anyway, so your diffusion will follow the same. So there's more vacancies, diffusion can occur faster.
Exactly. So at higher temperatures, you have higher concentration of the vacancies. And we just mentioned that the diffusion is typically driven by the vacancies themselves. So if you have more vacancies, that diffusion is more likely to happen. So this is a very intuitive way of describing this. But again, this particular diffusion coefficient follows the same Arrhenius behavior. And then you can plot this diffusion coefficient as a function of 1 over t, and it would have the same linear dependence as before. Okay, so I would just like to mention one particular example where this becomes very important. And you can even think about how these diffusivity or diffusion coefficients happen and how do they depend on, for example, different atoms. So in this particular example, you can see that the diffusion coefficient for interstitial atoms, example would be carbon in iron. Carbon is carbon is a very small atom, and it can really move throughout the iron material very quickly. And for that reason, the diffusion coefficient is relatively high in comparison to the diffusion of substitutional atoms. So what that means is that if you have an interstitial atom, it's more likely to diffuse throughout the material because it's easier for that atom to move than if you have substitutional atoms that require a lot of energy to move from one side to another. So you can see this, for example, you can have zinc in copper, and you can see that, for example, carbon is much easier to move throughout the iron than in this particular case. One example that I would like to point out as extremely technologically important is the question of the contacts. So I told you that this would be a typical transistor, right? And this is silicon material that has P and N region. So these lines on the surface are metal contacts that have to contact these individual regions of the material itself. So ideally, you would like these contacts to be as conductive as possible. So you need to run electricity through this material, right? So you would like to choose the material that is as conductive from the electronic perspective as possible. As it turns out, for example, copper and silver would be your materials of choice. But in this particular case, you can see that copper and silver have very high diffusion coefficients in silicon. What that means is that when you deposit them and, for example, increase the temperature, your transistor works in your computer, you're increasing the temperature, it's very likely that these metals would simply diffuse inside of the material. And you completely mess up this structure, right? So suddenly you have copper atoms that are interdiffusing in silicon, you are completely changing the electronic structure of silicon, etc. So how do you overcome this problem? What do you do? How do you make a contact that has relatively high electrical conductivity, but you prevent diffusion? What would you do if you look at this graph here? Yes?
Add a really big fan.
Yeah, okay, add a big fan. You do have fans in your computers. Okay, still computers fail sometimes. What do you do? Yes? Use aluminum. How would you use aluminum? Just use aluminum as a contact?
Put it in silicon.
In silicon? Okay. Okay, I mean, yeah, okay. Explain. What would you do?
You just put it on top of the silicon and constantly use it.
Okay. So you're going in a good direction. So you would choose aluminum because it has a very low diffusion coefficient, so it won't interdiffuse into silicon. However, it's not highly conductive, and it also oxidizes very easily. So you deposit a layer of aluminum to protect interdiffusion, and on top of that, you add gold or copper. So what that means is that you still have very good contact, but you really remove this problem of the diffusion. What this particular example tells you is the fact that sometimes you really want the diffusion to happen. For example, if you're forming a solid solution of materials, you're forming steel, you want to mix carbon and iron. Sometimes you really want to prevent it. So you really need to know what drives the diffusion and how you can prevent this from happening, right? So again, I can tell you that this was one of the major developments when people started to think about transistors in general. How do you make contacts, right? Okay, so with this, I would like to conclude and just tell you that basically the diffusion also depends on other types of defects. It turns out that the diffusion on the surface or diffusivity of the materials on the surface is much faster in the bulk. And I won't go into details, but if you're interested, there is a very interesting paper that actually talks about this, and it shows directly the alloying process in the material. But before we leave, next time we will talk about dislocations in materials, but I would just like to summarize what we learned today. So we talked about ionic point defects. And we specifically talked about Frenkel and Schottky. We talked about Kruger wing notation And we talked about doping in semiconductors. And specifically, we talked about diffusion as a process that happens when you have concentration gradients in materials, that sometimes it's enhanced and you want to enhance it, and sometimes you want to prevent it. But in any case, you need to know what is driving that process. Okay, so I will see you on Wednesday, and then we will start a discussion about dislocation.